A new,
That's
unprecedented
impossible.
image of 3I/Atlas has revealed something truly strange, causing a ripple of astonishment among scientists. They've discovered that sunlight behaves in a completely different way around this enigmatic object compared to anything we've ever witnessed or even dared to imagine before. What fundamental principles of light and matter interaction might this challenge? Just look at this fascinating image. It was meticulously captured by the Mastcam-Z camera, a sophisticated instrument aboard NASA's Perseverance rover, currently exploring the Martian surface. The picture shows a faint, almost ghostly blurry spot in the vast Martian sky, precisely the coordinates where scientists had predicted the interstellar object 3I/Atlas would make its appearance. This isn't just any snapshot. It marks the very first time humanity has ever laid eyes on 3I/Atlas from such a remarkably close distance, offering an intimate glimpse into this cosmic visitor. In the photograph, the comet manifests as merely a faint smudge, barely discernible, positioned right next to a cluster of distant stars, each glowing with an approximate dimness of magnitude 8. Further corroborating evidence, an additional piece of data, vividly illustrates something actively moving across the Martian sky, which scientists are confident is none other than the interstellar wanderer 3I/Atlas itself, carving its path through our solar neighborhood. Interestingly, this groundbreaking picture wasn't actually taken at the absolute moment of 3I/Atlas's closest approach to Mars. The diligent Perseverance rover managed to capture it a full day prior to that exact instant. Scientists have pointed out that the true, closest conjunction could only be properly observed and documented by Mars orbiters, which possess a more advantageous vantage point. However, due to some of NASA's current operational challenges and unforeseen issues, it may regrettably take some considerable time before they are able to process and subsequently release those highly anticipated, incredibly detailed close-up images of the object to the public. The suspense builds as we await these crucial visuals. During 3I/Atlas's near pass by Mars, the Perseverance rover's sensors also concurrently registered an intriguing increase in Martian surface activity. The image itself provides compelling evidence, showcasing several dust devils, miniature whirlwinds of Martian grit, energetically swirling around the rover's immediate vicinity, while a much larger, formidable dust storm could be seen ominously forming on the distant horizon. Could this heightened activity merely be coincidental, or did the interstellar visitor somehow influence the Martian environment? Remarkably, the telltale tale of this interstellar object isn't visibly depicted in the rover's images. It was simply too incredibly faint at that particular moment to be captured. Scientists have already engaged in extensive discussions about how this comet's initial appearance was unusually perplexing precisely due to its striking lack of a prominent, visible tail, a characteristic that is exceedingly rare when compared to the vast majority of comets we typically observe. However, as it continued its journey and approached closer to Mars, the comet did indeed begin to exhibit the nascent stages of a thin, ephemeral tail, though it remained significantly fainter and narrower than any comet tail ever recorded previously. This subdued tail still speaks volumes about its unique composition or activity. There are also tantalizing other images of 3I/Atlas that purport to show more intricate details of its overall shape, but it's important to note that these have not yet undergone full verification by the scientific community. Based on these unconfirmed, yet intriguing visuals, the comet appears to possess a distinctly elongated, almost spindle-like shape. This characteristic makes it bear a striking resemblance to the first ever interstellar object, Oumuamua, which famously baffled astronomers with its cigar-like form, and decidedly less like the more traditionally shaped interstellar comet 2I/Borisov. Recently, the interstellar comet 3I/Atlas undertook a fairly close celestial rendezvous with Mars, coming within approximately 0.19 astronomical units, a staggering distance equivalent to roughly 28 million kilometers away. It's now currently hurtling through the vast expanse of space at an astonishing velocity of nearly 200,000 miles per hour, relentlessly heading toward its closest point to the Sun, a critical juncture in its trajectory known as perihelion. However, things just took an unexpected and dramatic turn. Astronomers are now operating under the belief that 3I/Atlas may have been significantly affected by a coronal mass ejection, CME. A colossal burst of solar energy and billions of tons of plasma particles violently erupting from the sun's surface. Following this intense solar event, the comet quite suddenly vanished from observable view, a disappearance likely attributable to a combination of its rapidly increasing distance from Earth and the overwhelming glare of the sun. Furthermore, Earth is now dynamically moving in the opposite direction relative to the comet, a celestial ballet that makes it even more challenging to discern the faint object against the luminous background of myriad stars. Consequently, 3I/Atlas, this elusive cosmic traveler, won't likely become visible again to terrestrial instruments until later this year. And just when many in the scientific community, and indeed the public, had begun to settle into the idea that this might, after all, be a somewhat normal, albeit interstellar, comet, recent new observations have unveiled a series of totally unexpected anomalies in both the comet's intrinsic structure and its peculiar light behavior. These are not minor deviations. These features directly challenge and potentially rewrite what we currently understand about the fundamental physics and formation of such celestial objects. What deeper secrets lie within this cosmic enigma? Astronomers have, with pioneering effort, recently conducted the first ever polarimetric observations of the interstellar comet 3I/Atlas. To truly grasp the significance of this, consider how sunlight behaves. When it travels through the vacuum of space and encounters an object like a comet, the light doesn't simply bounce straight back in a predictable manner. Instead, it scatters, diffusing in countless directions. Each microscopic dust grain or tiny ice particle suspended in the comet's coma acts like a myriad of minuscule mirrors, subtly yet profoundly altering the way the light interacts and behaves. When this scattered light then strikes something, for instance, the expansive cloud of dust surrounding a comet, those light waves, which ordinarily oscillate randomly in all directions, can become significantly more organized. Instead of haphazard movement, the waves begin to align themselves, propagating predominantly in certain, specific directions. This fascinating phenomenon of light waves lining up is what we scientifically refer to as polarization. By meticulously measuring precisely how much the light becomes polarized and, crucially, in which specific direction this polarization occurs, astronomers can glean an astonishing wealth of information about the very dust it reflected off. This includes details such as the dust's average size, its intricate shape, whether its surface is rough or exceptionally smooth, and critically, its fundamental composition, whether it is predominantly made of ice, rock, or perhaps an enigmatic mixture of both. It's like reading the comet's autobiography through its scattered light. When scientists routinely observe comets that originate from within our own solar system, they typically detect a phenomenon called positive polarization, especially when the comet is viewed at larger phase angles, the angle between the sun, the comet, and the observer. Conversely, at smaller phase angles, many of these familiar comets tend to exhibit negative polarization. However, when astronomers turned their sophisticated instruments toward the interstellar comet 3I/Atlas, they were met with an astounding finding. Its negative polarization was not just present, but extraordinarily strong. In fact, vastly more pronounced than in any comet we have ever observed before. This discovery was not merely surprising, it was a profound shock to the system. It fundamentally implies that the dust grains that comprise the coma of 3I/Atlas are radically different from those found in the comets that call our solar system home. They might possess surfaces that are significantly rougher or exhibit far more irregular, fractal-like shapes. Alternatively, they could be composed of entirely novel materials, substances that are incredibly rare, perhaps even utterly unknown, within our familiar celestial neighborhood. This observation is monumental, marking the very first time we have ever witnessed such anomalous polarimetric behavior in an object originating from beyond our solar system. While the scientific community has had the privilege of studying numerous comets from our own solar system, and even a handful of other interstellar visitors, none, absolutely none, have ever exhibited the truly unique polarimetric characteristics so strikingly evident in 3I/Atlas. Its extreme negative polarization, specifically recording a minimum of -2.77% at a phase angle of just 6.4 degrees, is not merely unusual. It is genuinely unprecedented among all known comets, presenting a cosmic puzzle of extraordinary proportions. This profoundly strange behavior offers a powerful hint that 3I/Atlas could have originated and formed in a completely alien kind of environment, one starkly different from anything within our solar system. Perhaps it coalesced within the frigid depths of another star system altogether, or possibly even from the extreme, icy fringes of our very own solar system, where conditions are dramatically colder and far more conducive to exotic ice formation. Scientists have previously put forth the intriguing claim that this object is, in fact, older than our entire solar system itself. According to their extensive research, it most likely embarked on its journey from the inner, denser regions of our galaxy, thereby solidifying its status as one of the most ancient and profoundly mysterious visitors ever observed gracefully passing through our familiar solar neighborhood. In yet another astonishing observation, scientists have detected an unusual and strikingly similar chemical composition around this enigmatic object. They found that the immediate environment surrounding this interstellar visitor bears an uncanny resemblance to the atmospheric and surface conditions found on our neighboring planet Mars. This remarkable similarity strongly suggests that the object did not originate from a typical comet-forming region, such as the distant Kuiper Belt or Oort cloud within our own solar system. Instead, a more audacious hypothesis suggests it might have originated directly from a planetary surface, conceivably from a world with environmental conditions strikingly akin to those found on Mars. Could it be a fragment of a lost planet from another star system, ejected and sent on an interstellar voyage? Some observers even claim that the object appears to glow in strange, unearthly ways, emitting light in patterns not seen in regular comets. This peculiar luminescence might signify that as it draws nearer to the Sun, it could undergo a far more intense process of evaporation, shedding its material at an accelerated rate, or even potentially fracturing and breaking apart into multiple pieces as it approaches its perilous perihelion. Scientists have also observed other mysterious behaviors emanating from this object, adding to its growing list of cosmic curiosities. We've already taken note that 3I/Atlas is actively losing mass as it's enveloped by a visible cloud of. When a comet typically sheds gas, it's a process of sublimation where volatile ice within its nucleus heats up and turns directly into gas, creating a diffuse atmosphere known as a coma. This release of material acts much like a minuscule propulsion system. The escaping gas imparts a tiny but measurable thrust, subtly pushing the comet off its expected orbital path. Picture a rocket continuously firing a series of almost imperceptible thrusters. Yet, the interstellar visitor, 3I/Atlas, defies this fundamental cometary physics, behaving in a remarkably anomalous manner. Even as scientists observe significant gas clouds forming around its nucleus, indicating substantial outgassing, its trajectory, paradoxically, appears utterly unaffected, holding steadfastly to its course. How can such a massive expulsion of material produce no discernible deviation? This perplexing lack of orbital perturbation, some scientists theorize, could actually be a profound clue, hinting at the object's truly enormous mass. The sheer inertia required to resist the propulsive forces of outgassing suggests that 3I/Atlas isn't just large, but incredibly dense and heavy, far exceeding prior expectations for any celestial body of its kind. Indeed, initial estimates were already staggering, proposing that 3I/Atlas could be at least 1,000 times more massive than any comet ever observed in our solar system's history, dwarfing even our largest known cometary behemoths. More recent, refined studies have pushed these figures into the realm of the truly mind-boggling, estimating its total mass could exceed an astonishing 33 billion tons, an almost unimaginable, unprecedented amount for what we typically conceive of as a naturally formed comet. This raises a critical question. What kind of natural processes could forge such a colossal, dense cometary object? Moreover, this colossal mass presents another profound enigma. Not only is 3I/Atlas orders of magnitude more massive than any previously encountered comet, but astrophysicists contend that there simply isn't an adequate reservoir of rocky material dispersed throughout interstellar space to naturally aggregate and deliver such a gargantuan object into the inner solar system within the last decade. The sheer scarcity of dense, rocky components per unit volume in the vast emptiness between stars makes the existence of a naturally formed object of this scale, arriving precisely when it did, a statistical improbability that borders on the impossible. Recently, Professor Avi Loeb, a renowned astrophysicist, meticulously organized all the bewildering observations surrounding 3I/Atlas into two distinct, thought-provoking categories. In the first category, he cataloged a series of anomalies that, while currently puzzling, might potentially yield to explanation with the acquisition of more comprehensive data in the future. These include its colossal size, which, though immense, might eventually be understood within extreme parameters of natural formation. Then there's the peculiar anti-tail, which, instead of pointing away from the sun as typical cometary tails do due to solar wind and radiation pressure, seems to point towards the sun, a visually disorienting phenomenon. Another intriguing feature is a forward jet of scattered sunlight, an elongated plume approximately 10 times longer than it is wide, also inexplicably pointing directly toward our star. Its unusual chemical composition, featuring an unexpected abundance or scarcity of certain elements, also falls into this category, as does its strong negative polarization of light, a signature that deviates significantly from what's expected for a typical comet and hints at complex scattering properties. However, it is in the second category that Professor Loeb placed the truly profound anomalies, those that may, quite literally, remain baffling forever, challenging our fundamental understanding of random cosmic events. Foremost among these is the extraordinary alignment of 3I/Atlas's trajectory with the ecliptic plane, that cosmic racetrack or flat disk where all the planets in our solar system meticulously orbit the sun. To find an interstellar object arriving randomly from the depths of space, aligning its path within a mere 5 degrees of this specific plane is, statistically speaking, an incredibly improbable and highly suspicious coincidence. Furthermore, as if orchestrated by some unseen cosmic conductor, the arrival time of this interstellar visitor appears to have been perfectly synchronized to pass remarkably close to no less than 3 major planets: Mars, Venus, and Jupiter. What are the odds of a randomly arriving object performing such an elegant, almost choreographed, gravitational dance with multiple planetary bodies? Even more profoundly, and perhaps most startlingly, the direction from which 3I/Atlas emerged is aligned within a chilling 9 degrees of the infamous WOW signal, detected on August 15, 1977, by the Big Ear radio telescope. The WOW signal was an incredibly strong, narrowband radio transmission, lasting 72 seconds, which so profoundly matched the expected characteristics of an extraterrestrial signal that it prompted astronomer Jerry Emmon to famously write "Wow" on the printout. Some scientists at the time genuinely considered it a potential message from an intelligent extraterrestrial source, a one-time event that has never been repeated or fully explained. The statistical likelihood of a randomly arriving interstellar object originating from the exact same direction as this singular, unexplained signal is, by any natural measure, staggeringly low, defying mere chance. Professor Loeb, therefore, has consistently argued that those who staunchly maintain that 3I/Atlas is merely an ordinary, naturally formed comet bear a significant scientific burden. They must be held accountable to provide a comprehensive, rigorous explanation for this cascade of unusual coincidences and highly improbable alignments, not just individually, but collectively, through purely natural, unassisted processes. The confluence of these anomalies, he contends, makes a purely natural explanation increasingly strained and difficult to sustain.